25, Properties of Integrals and the Second Fundamental Theorem. This section is pretty challenging in that a lot of the problems require you to understand like theorems, or basically vocabulary. So a lot of times I talk about the AP tests. A lot of the challenge of it isn't knowing how to do the calculus, it's knowing when to apply the calculus. They'll phrase questions in ways that maybe you haven't seen before, where calculus can be useful to solve for the answer, but you need to know which tool to use. And so this is a section with a lot of tools. So the two big things are the second fundamental theorem of calculus and then just the smaller integral rules from section 4.3. So the second fundamental theorem of calculus, as our book says it, is that if you take the derivative of the integral of a function, what you get is the function back, except instead of having t plugged in, now we have x plugged in. This is easy to show if we just get a basic problem. So I'm going to take the derivative of the integral. Instead of having a there, I'm going to throw a number there, so I'm going to throw 2 there. It doesn't really matter what I put there for the sake of this. Okay, so I'm going to say f of t is 2t. So I'm going to write that over here. F of t equals 2t. So we know that our end result, if this works, should be x squared. So let's see if we get it. So d over dx of this nonsense. Let's integrate this. Our integral is going to be from 2 to x, and we're taking the derivative eventually, of t squared. Pretty easy definite integral. Plug in x squared. So we get, or plug in x into this, we get x squared minus 2 squared, which is 4. And now we're taking the derivative of this. I got a little messy. I'm going to fix this real quick. So we go from there to here. The derivative of x squared minus 4 is just 2x. And booyah, we did get exactly the same thing as we started with, except with x plugged in instead of t. Now, there's more to the second fundamental theorem of calculus. There's some harder kind of problems, but this is the base idea for the second fundamental theorem of calculus, is that you just get the same thing out except with the number plugged in. And another important thing to note is that this constant here didn't matter, because when we plugged it into the definite integral, what it gave us was a number, because that's what we get when we plug numbers into the definite integral. We just get like 4. It didn't matter if this was 0, I would have gotten 0 there. Derivative would have been the same. I could have had 100 here. I would have gotten 10,000. Derivative of 10,000 is still 0. So that bottom number doesn't really matter. That's why it's a in the equation. It doesn't matter what it is. Okay, so the other thing in our section is the rules of integration. I have a list of them here. So you can pull out a constant if there's a constant within the equation. For example, if you have the integral of 8x squared, you can just pull the integral, or dx. You can just pull the 8 out in front. So you can just have 8 times the integral of x squared dx. Pretty easy. Negation, we can swap the bounds and throw a negative sign on. So that means that the integral from 1 to 2 of f of x, well, no, let's like actually make a function here, of 2x dx is the exact same thing as negative of the integral from 2 to 1 of 2x dx. So when we swap the bounds, all it does is make it negative. Third one, decomposition. This one is pretty picture dependent. Basically, if we have a graph up here, say we're starting from here to here, our graph's up here in space, like so. I'll zoom a little on that. And then I pick some point in between, so that's what the C is that they're talking about here. So from A to B is where our interval is. They're saying we're cutting it at C, and if we add this integral to this integral, we're going to get the whole integral. It makes a ton of sense with the picture. You're just adding two areas together instead of actually just figuring out the whole area. Our fourth one is addition. If we have addition happening inside our integral, we can split it into two integrals. So for example, if I have the integral from 1 to 2, we'll just throw some bounds on here, of 7x squared plus 6x dx. This is exactly the same as the integral from 1 to 2 of 7x squared plus the integral from 1 to 2 of 6x dx's. Whoops. So, yeah, you can split up addition. You can't split up multiplication. Remember, we have no product rule, no quotient rule, no chain rule in integration. And our last thing is the zero integral. If the top and bottom bounds are the same, our integral is 0. Another one that makes a ton of sense if we go back and look at our picture. If we're going from A to A, we're not passing any distance. It means the thickness of our box or shape that we're finding the area of is 0, and anything with a thickness of 0 has a area of 0. So yeah, that one's no good. Cool. Those are all the rules. Let's solve some problems. So start with the first problem I threw on here. I said the integral from a to b of f of x is 2a minus 5b. Then I said, what is the integral from a to b of f of x minus 2? This is one where we want to use, let's go back to our rules, the addition rule. We can split it into two integrals because there's addition in this. So I'm going to go back and I'm going to split this into the integral from a to b of f of x dx minus, or we'll just do plus, the integral from a to b of negative 2 dx. Cool. I know this answer. It's 2a minus 5b. Tell us in the problem. This second thing, well, I got to integrate it. So a and b are my bounds. If I integrate this, I get negative 2x. Now I got to plug in my bounds. I get 2a minus 5b plus negative 2b, if I plug in the top bound, minus a negative 2a. So really, that's 2a plus 2a minus 5b minus 2b. So 2a plus 2a is 4a. And negative 5b minus 2b is negative 7b, and we have our answer. That's it. All right, second one. Okay, this requires even more than just our second fundamental theorem of calculus we talked about before. It requires a more general case. The more general case is that if we raise something instead of just to x to some function of x, like we have x squared in the problem that we have over on the other side, our derivative is just going to be equal to f of x squared. F of u of x is that thing if it's x squared. It's x squared. Times the chain rule. So really the added part is we're plugging in this thing and then we're doing the chain rule. So the chain rule of x squared is just 2x. So my answer should just be x squared plugged in where t was in my original function. And then I just multiply by 2x. So I'm going to go do that over here. Oh, sorry, y in this equation. So I'm going to plug in x squared for y, and I'm going to get x to the 6th minus 2x squared. That is f of x squared from the second fundamental theorem of calculus. And now I just multiply by 2x. So times 2x. Now this problem says I'm not done. This is the derivative. This is indeed f prime of x. And our last step is to go, okay, I just plug in 1. 1 minus 2 times 2. Well, that's -1 times 2 is -2. One thing I neglected to point out is that this is a second fundamental theorem of calculus, even though it doesn't have a derivative written. Just to remind you, there's a derivative of an integral happening here. But I imply the derivative by giving you f of x and then asking for f prime of 1. So I'm asking you to take the derivative of the integral. And this is why you should know that it's the second fundamental theorem of calculus. Also, like I write it in what the section's named. Okay, few more examples. The integral from 5 to 5 of this nonsense. Yeah, the answer is just 0. Integral from same number to same number of anything is just 0. And our last one, integral from 5 to 2 of f of x. Here, I have these rules up here, so I know what f of x is. F of x from 1 to 2 is -4. F of x from 1 to 5 is 6. So I'm going to use this information to solve this problem. So, I know over the whole thing it's 6. And I know from 1 to 2 it's -4. And so I actually don't want that part. I'm only going from 2 to 5 on my interval. So I'm going to do 6 minus a -4, which is 10. And that's the integral from 2 to 5 of f of x. And there's no dx here. That's pretty weak. But that's not what the question's asking for. The question's asking for the integral from 5 to 2. So we have to go back to our rules of integrals, which is the negation one. If we swap the bounds, we just make a negative. So our answer shouldn't be 10, it should be -10, and so our answer is just -10. So we use quite a few of those rules in that table. The fact that the decomposition one, where we can split an interval in parts and figure out the other parts. So we knew like the integral from 1 to 5, we subtracted off the part from 1 to 2, which I could like show a picture of. From 1 to 5, we have an integral of something, and I just hacked off this part. Go away. That's from 1 to 2. And I'm left with from 2 to 5 there. But because, say this was accurate and this area is 10, from 2 to 5, if I go from 5 to 2, I'm going backwards. I'm actually going to be de-accumulating this. It's going the opposite direction, so I'm going to get -10 as my answer. This is a heavy section. There's a lot of stuff in it. Make sure to know the second fundamental theorem of calculus. Make sure you're very comfortable with these rules. Make sure you're very comfortable plugging in variables into definite integrals. It works the same as numbers. You just plug in b instead of like 7 or something like that. And it's actually easier because you don't need to simplify them. But yeah, that's all the stuff in this section.